Hello, AP Chemistry. How are we doing today? Hopefully y'all are doing well. So today we are going to be continuing our Unit 7 notes on equilibrium. And today's topic is going to be LeChatelier's principle. So what is LeChatelier's principle? Well, basically all it says is that when we apply stress to a system, the equilibrium is going to shift to relieve that stress. And so I tend to think of this kind of like a seesaw. If I've got more of a reactant, then it's going to shift to favor those products, for those products to become more, right? And if I've got more of a product, then we're going to see that shift in the other direction. So reactants add more, they're going to go lower, right? And so as a result, to fix that, I'm going to have to change these into products. So change my reactants into products and cause that shift to occur again, okay? Now what happens if I overproduce and now I've got more products? Well, then I would have to see that shift come back until eventually this keeps on going until we reach equilibrium, okay? So let's actually take a look at what's going on. So first off, changes in concentration. So what does this mean? Well, this means if I add some more reactants or products, what will it do to my equilibrium? Well, it's exactly what we said with this seesaw. So if I increase the concentration of my reactants, this will cause my equilibrium to shift to the right, which makes us form more products. So an increase in that concentration of the product will cause that equilibrium to shift to the left to form more reactants, right? And so basically we're just going to keep doing this seesaw thing until eventually we get to that point of equilibrium. Now, what happens if I decrease my concentration of the products? Well, if I decrease the concentration of the products, that will cause my equilibrium to shift to the product side so that we would form more products, okay? If I decrease my reactants, then it would shift to the left side, the reactant side, to form more reactants, okay? Again, think seesaw. I cannot stress this enough because the seesaw has helped me so many times with equilibrium, just determining which direction this reaction is going to proceed, okay? So let's take a look at this. This is kind of a conceptual way of looking at this. So a change in concentration of reactants or products will not affect the value of K, okay? So we're not going to actually affect the value of K, which is that equilibrium constant. So let's look at this. So here's my reaction. A plus B in a reversible reaction produces C plus D. So if I add A or B, if I add one of these, well, those are my reactants, right? So if I add a reactant, we're going to see a shift right to form more product. So that's all we're doing, is we're going to be looking at these and seeing, okay, well, how is this going to affect my equilibrium? So if I remove A or B, again, those are reactants. So if I remove some reactants, then I'm going to see that shift to the reactant side to form more reactants, okay? So I actually want y'all to go ahead and give these next few, I want y'all to complete add C or D, remove C or D, and then I actually want you to go ahead and move on down to an actual example of a chemical reaction and do the same thing. So if I add reactants or products, what direction is that going to shift? Okay, so pause your video, solve these next couple, and then we'll go over it. All right, so let's take a look at this first set here. So it says remove A or B. Again, we talked about that. We would see a shift to the left to form more reactants. Why? Because we removed some of the reactants. Well, now what if I added some product? Again, I would see that shift to the left so that I would form some more reactants. Again, I added more products, right? So that would shift my equilibrium, which would cause more reactants to form, okay? What happens if I remove my products? Well, if I remove my products, it becomes reactant heavy, and so then we would shift back to our product side to form those products, okay? All right, now let's take a look at this kind of real world example. So I took N2 plus 3H2 in a reversible reaction to produce NH3. So in the addition of N2, well, again, that's a reactant, so we would shift to the right to form some products. Addition of NH3, that's a product, so we're going to shift to the left to form some reactants. What happens if I add H2? Again, that's a reactant, so we're going to shift to the right to form some products. And then Removal of NH3, so I'm taking away some products. So I'm going to shift to the right to form some more products. Okay, so pretty straightforward. Again, just follow that seesaw. Whatever direction you're seeing an increase, the other side is going to adjust to make up to reach that equilibrium. Okay. All right, so that's going to be changes in concentration. So let's take a look at something else that could affect our equilibrium. Changes in temperature. So changes in temperature may be easily treated if you think of my heat as a product or reactant. So remember, in an exothermic reaction, we are releasing heat, right? And so that's going to be on the product side. And so we can think of it as a product. So if I add heat in an exothermic reaction, then we're going to see a shift in which direction? We're adding more products, so we're going to see it shift to that reactant side. Now, what about a endothermic reaction? Well, an endothermic reaction, your heat is a reactant. And so since heat is a reactant, if I add some heat in endothermic, then I would see a shift to the product side to form some more product, okay? Now, here is something that temperature does that none of these other changes will do, and that is it will change K. So when we're looking at temperature, an increase of temperature in an exothermic reaction, which remember, exothermic means your heat is a product, will cause that equilibrium to shift to the left, but it will decrease your K, okay? So it will decrease the K. A decrease in the temperature in an exothermic reaction will cause it to shift to the right, and it will increase your K. So basically, when you're changing your temperature, you're favoring one reaction over another, which is going to result in that shift of KEQ, and it's going to cause a new equilibrium with its own KEQ, because remember, we can't really compare KEQs, right? So just know that if it's an exothermic reaction, that increase in temperature will cause my KEQ to decrease. Now, what about endothermic? Well, in an endothermic, if I increase my temperature, that's going to cause my equilibrium to shift to the right, right? Because my heat is going to be on the reactant side. And so my K is going to increase. So endo versus exo, you're going to have to remember that how they affect your K value is going to be opposite of one another. Okay, which makes sense, right? Because they are opposite in terms of how we or how they are dealing with heat. One is absorbing heat, one is releasing heat. Okay. Now, one thing I do want to remind you of before we actually go into pressure is that a big K value is product heavy. And a little K value is reactant heavy. All right. So that should help you a little bit with your temperature and seeing how those will affect your K values. All right. Next one, changes in pressure. So what happens if we change pressure in a system? Well, changes in pressure only affect your equilibrium systems having gaseous products and or reactants, okay? So when we talk about that change in pressure, we're basically just going to say, okay, this only really matters if we're talking about gases. So if I'm increasing the pressure in a gaseous system, what this is going to do is this is going to cause the equilibrium to shift to the side with fewer gas particles. Okay. Again, we're trying to cause this equilibrium to be reached, right? And so if I've got fewer gas particles over here and more over here, what I do is I see that shift in the equilibrium to cause this pressure to basically balance out. Okay. So there's less particles over here. So we're going to shift more of that pressure to this side. We're going to cause those particles to move a little bit more, which is basically going to mean these products over here are going to move a little bit less, right? And so we would see that pressure change. We would see that decrease in the pressure, okay? Now, what happens if I decrease the pressure in a gaseous system? So decreasing the pressure in that system will cause the equilibrium to shift with the side with more gas particles. And you're like, okay, well, how does that make sense? Well, so think about it this way. I've got a bunch, very few particles here, and a lot, sorry, I'm trying to show my hand, a lot of particles here. So very few and a lot. So if I decrease my pressure, what's going to happen? Well, I'm going to see that shift over to the side with more to try to see that decrease in pressure overall over the entire system. Okay, so do keep that in mind when we're talking about those changes in pressure. If we increase that pressure, it's going to shift to the side with fewer particles. And if I decrease the pressure, it's going to shift to the side with more particles. Okay, now here's something to know. If the system has the same number of moles of gas on each side, then changes in pressure will not affect equilibrium. Well, let's look back at this. If I increase the pressure in a gaseous system, it causes it to shift to the side with fewer particles. Well, if they've got the same number of particles, then we won't see a shift at all, right? Same thing with my decrease. Decrease in pressure with more particles. So if the system has the same number of moles on each side of the reaction, changes in pressure will not affect my equilibrium, okay? The other thing, adding an inert gas does not affect equilibrium since the partial pressure of the gases in a reaction are not affected. Why? Because those are inert, right? So they will not react. And so we will not see a shift in that equilibrium, okay? All right, now, something to note, changing pressure does not affect the value of K, okay? Changing pressure does not affect the value of K. The only thing that we're going to see that will affect the value of K is our temperature. So just make sure that you know that how that temperature will affect your K values, okay? So let's look at this. What if I were to add a catalyst to a system? What would that do? Well, the catalyst, remember, does not actually participate in the reaction. And so since it doesn't participate in the reaction, it will not affect our equilibrium, okay? All right, so let's take a look at this and see how these stresses are going to affect our equilibrium. So here's my reaction. It says, consider the reaction 2NO2 in a reversible reaction produces N2 and 2O2, which is exothermic. Okay, we know that that is actually important with equilibrium, right? A vessel contains NO2, N2, and O2 at equilibrium. And again, those are all gases. Predict how each of the following stresses will affect the concentration of O2 and the value of K. So first off, I'm going to add some NO2. Well, NO2 is a reactant. And so since NO2 is a reactant, we will see a shift to the right to form more products. So that shift to the right to form some more products. Now, what happens if I remove my N2? Well, N2 is a product. So if I take away some product, then what am I going to see? Same thing. I'm going to shift to the right to form some more product. So before we actually move on, I actually want y'all to go ahead and give this next few, so these next 4, a try. So this is just based off of those previous rules that we talked about. I want y'all to pause your video, solve these next 4 problems, and then let's go over them. Okay, so let's look at this. So here I've got the volume, or for C, the volume is halved. So what happens when I half the volume? Well, if I half the volume, I'm going to be increasing my pressure, right? Well, how does that affect my equilibrium? Well, when I increase my pressure, I know that there's going to be a shift to the side with fewer gas particles. So how do I know how many I have? So on my reactant side, I've got 2 particles. On my product side, I've got 2 here and 1 here. So I have 3 over here and 2 over here. So I'm going to shift to the side with fewer, which means I'm going to shift to my left to form some more reactants. All right. D, helium is added. Well, helium is inert, right? And so we know that when we add an inert gas, that's going to have no effect. Increasing my temperature. Well, remember with an increase in temperature, that does depend on if it is endo or exothermic. And in this reaction, they told us it is exothermic. So if I increase my temperature, what I know is that's going to cause the shift to the left to form some more reactants. Okay? Now, we also know that that would change our K value, right? We know that that would decrease that K value. Okay? Next, adding a catalyst. Well, adding a catalyst does not affect the overall reaction. It does not actually, or does not affect our equilibrium, right? Because all it's doing is it is lowering that activation energy, right? So there is no actual change in my equilibrium there. So no effect. All right, y'all. This next section right here is entirely practice for you. I highly suggest that you go in and do this, all right? So if you need to pause your video and do this, now is the time. I'm actually going to make a key of this online so you can double check your answer key. But otherwise, we're going to go ahead and move on. All right, y'all. So this thing right here, this is actually an FRQ. I want y'all to actually work through this entire FRQ, and this is based off of everything we've done so far in equilibrium, and solve the problems and then double check the key. This is fantastic practice for y'all in terms of preparing for your quiz later on, okay? So make sure to do this today, but I want y'all to go through and answer all of this FRQ, all right? So y'all, that is it for this set of notes. If y'all have any questions, please don't hesitate to reach out. As always, I hope y'all have a great rest of the day. Bye, y'all.